All right, so now I want to take our discussion that we had from last time about equilibrium and Gibbs free energy and talk about chemical equilibrium, particularly looking at a general chemical reaction. And so let's take a general or a more generic chemical reaction of formation. So let's say we have a metal in its solid state plus a gas, so X as a gas, and it's a diatomic gas, like oxygen, for example, and it forms a ceramic material MX. And so because of that, this is a solid, and this gas, you only need 1/2 of it. All right, so we have a change in Gibbs free energy for this reaction. So I'm going to abbreviate the reaction part here. So this is the Gibbs free energy associated with the reaction, right? So we're talking about going from one state to the next. So this state, the reactants to the products, and so the change is the change from this. So the change in free energy will depend on the states of their reaction, and therefore it's going to depend on the changing pressure of the gas, right? So the partial pressure of X2 will drive this reaction in one way or the other, as we've learned in general chemistry classes. And so we can write the change in Gibbs free energy for this reaction, like we saw for chemical potential, as the change for its standard state components plus RT natural log of K. So this is similar to what you saw for chemical potential, but we're using the reaction Gibbs free energy, and then we introduce this term K. So just a refresher, this is going to be free energy change with the reactants at their standard states. And K here, this is known as the equilibrium constant for the reaction. And it's defined, K for this reaction, this generic reaction that we have up here, is defined by activities. So this is why we talked about activities last time. And it's going to be the activities of the products, so activity of MX over the product of the activities of the reactants. So we have A sub M, so the activity of the metal M. And then because we define the activity of a gas by its partial pressures, then we can simply replace that with the partial pressure of that compound. And all of these are raised to the coefficients out front. So all of those were 1 except for this. So the pressure is raised to 1/2 for this case. So this is known as the mass action expression. This equilibrium constant expressed in terms of activities, but we're going ahead for the gas and subbing in the partial pressures. And remember, our definition of partial pressures was partial pressure, or the activity is equal to the partial pressure over its standard state, which was 1 atmosphere. So inherently there's a divided by 1 atmosphere in this expression here. Okay, so again, this px squared is, we're subbing in, is actually the activity of x squared. So that's essentially what we're writing is this. But this is 1 atmosphere by definition. And so since this is the case, we can just sub in the pressure. The other kind of note that we can make here is that the activity of pure solids and liquids, so anything we call in the condensed state, so liquids and solids, is to be unity, or again, 1. So any pure solid or liquid, so again, pure is the important thing here, is equal to, has an activity equal to 1. So that's an important thing that we can sub in with these expressions. All right, so since we are talking about equilibrium, at equilibrium, we know that by definition, the Gibbs free energy the change in Gibbs free energy is going to be 0. Sorry for the zoom again. So we know that this quantity is going to be equal to 0. And therefore, we can sub that into our expression for the reaction, and we get that delta G of the reaction at its standard states is equal to minus RT natural log of the equilibrium constant, or the mass action expression at equilibrium. Okay, so we did an example here for that generic formation of a ceramic, but let's sort of make it even more generalized. So let's take a reaction of A plus B, and we have coefficients out front of lowercase a and b, and that goes to C plus D. So the coefficients out front are all the lowercase of the letters. So in that case, then the mass action expression can be generalized to the activity of C raised to its power C, multiplied by the activity of D raised to the power of D, and then over the same thing, the product of the reactants. So activity of A to A, activity of B to B. So this is the more generic version of the mass action expression for, again, this reaction here.